pass the baton over to Ron. And I think, Ron, it should be yours now to take over. Yes, I see not full screen yet, but there we go. There's
when you see the title screen.
Yep, it's up and running.
Okay.
So take it away.
All right, great, thank you. So welcome to my presentation on improving bus predictions using machine learning. I'm Ron Mock, and I'm the software development manager at TransLink, and we're based out of New Westminster, BC, Canada. Some quick facts about TransLink if you're not familiar with us. So TransLink is the regional transportation authority for Metro Vancouver. And so this covers Vancouver and the surrounding suburbs. As such, we are Canada's largest transit service area at 1,800 square kilometers. And we serve a total population of 2.5 million people. A quick overview of TransLink's fleet. So we have SkyTrain. This is our rapid transit system, which is the longest in Canada at 79 kilometers. It's also one of the longest fully automated driverless systems in the world. We have a small fleet of 3 passenger ferries, which connect Vancouver and North Vancouver. And finally, we have buses that serve over 200 routes with over 1,500 vehicles in the fleet. In 2018, there were 262 million bus trips across our network. Now, with that many trips, a lot of our customers want to know when the next bus is leaving their stop. So how do we convey that information to the customer? So TransLink has several ways to let the customer know when the next bus is leaving their stop. We have a NextBus SMS service where the customer can text their bus stop number to us and then they get the predicted time back. They can go directly to TransLink's website and use our NextBus web app. They can use Google Maps, and they can use other third-party applications such as Transit App or Radar. Okay, so that's how the customer can get the NextBus information. But what exactly were we giving them? So the NextBus predictions were based on AVL data. And so if there was a difference between the bus leaving a stop and the scheduled time, that difference would simply be applied to the schedule. So for example, if a bus was 2 minutes late at a stop, our prediction would be the scheduled time plus 2 minutes for all the subsequent stops. So this prediction would be updated every time the bus leaves or passes a stop, or every 90 seconds, whichever came first. Now, while this system is simple and very fast, it does not take into account real-world situations such as weather or traffic. And this system is what we call our RTTI system. And so for simplicity, just think of RTTI as our old way of doing predictions. Okay, so what's the problem then? So we have real-time NextBus predictions, but they're not always accurate. So what does that mean to our riders? Well, here's a sample of some real tweets we've received. And I've had to censor out some of the more colorful language, but it's pretty clear, a lot of customers were unhappy because their predictions were not accurate. So let's quantify this problem. So this graph shows the actual bus departure time, the red line in the middle, versus the RTTI prediction, the blue pyramid. So the blue bars to the left of the red line indicate the prediction was too early. The blue bars to the right of the line indicate the prediction was too late. And each increment on the x-axis equals 1 minute. Now the green box, you can see that's it spans one increment to the left of the line and 3 to the right. So this green box represents where the prediction was on time according to transit standards. So this means it was at most 1 minute early or 3 minutes late. So this prediction is considered very good by the customer. Ideally, we want as many predictions as we can get to fall within this green box. Now, the yellow box represents predictions that are within plus or minus 5 minutes of the actual departure time. So this is the threshold where the customer considers it okay, but it's not great. Anything outside the yellow box means the bus is either more than 5 minutes late or more than 5 minutes too early, according to our prediction. So at this point, the customer is considered in the dark. This means it doesn't matter if the bus is 5 or 15 minutes late. It feels the same to them. Now, as you can see, only a little more than half of the RTTI predictions fell within the green window, and about 80% of the RTTI predictions were in the OK box. This means close to 20% of all predictions were in the dark, hence the angry tweets. Clearly, we needed a better way to generate predictions. So we broke down the problem into the simplest components. We wanted to know what the time it would take from a bus to get from stop A to stop B. So we'll call this a segment. How long is it going to take to traverse this segment? We will call this length of time the runtime and approximate it with a runtime model. Now, what are the things that can impact the runtime? Let's have the model take into consideration the weather, the date and time, previous runtimes for this segment, and we purposely did not include scheduled time so as not to bias the model. So these are the components of our runtime. Now, what about when the bus reaches the stop? Some stops will take longer to load than others. Let's call this the dwell time and approximate it with a dwell time model. The dwell time will also take into consideration the same factors, so weather, date, and all that. So, so the predicted departure time at stop B is the current time plus the runtime plus the dwell time. So if we break it down this way, it's fairly simple. Now, I mentioned we take the weather into consideration. Now, for that, we use the Dark Sky API for real-time and forecast data. Now, to simplify things, we divided the transit region into 13 geographic-based weather regions. For example, we'll assume all segments and stops in Richmond will experience the same weather. So this just kind of speeds up the system a little bit more. The Dark Sky API offers a full collection of weather conditions. So we used, a whole bunch of parameters in our models. We used all of these. I'm not going to go into detail, but you can tell how many weather conditions that we take into account. So the machine learning model that we chose was Extreme Gradient Boosting, XGBoost. And we chose this because of its fast training time and high performance rate. I won't go into the further detail on XGBoost as it is outside the scope of this presentation. Now, each bus stop and segment in the transit system has their own set of machine learning models, provided that there's enough data to train on, which should be 500 instances of dwell and run events. For those stops or segments that didn't have enough data to train a model, we defaulted to either scheduled data or RTTI. Now, as we create and train a different sets of XGBoost models for every single segment and bus stop in our system, we'll end up with over 18,000 sets of models. Now, with machine learning models generating prediction times for individual segments and stops, we need to create an algorithm that aggregates these predictions together to create stop and arrival departure times for particular buses. This is the bus level prediction. Unsurprisingly, we call this algorithm the aggregator. Now, every time there's new information about a bus location or weather that's received in our system, these bus level predictions are recalculated using the latest relevant model level predictions. So let's put this into a picture. It'll make things a little bit clearer. So this is what the bus level prediction looks like in action. Remember, the bus level prediction is an aggregate of all our model level predictions for that route. So if I'm a rider at stop F, the prediction I get is the sum of all the run and dwell times plus the current time. These individual times are updated every time the AVL system is updated by any bus on the route. So when the bus leaves stop B, the system will recalculate all of the subsequent run and dwell times, and then I'll get an updated prediction. Note that I said the model level predictions are updated for any bus on the route, not just the specific one I'm waiting for. So for example, if I'm waiting for the number 14 bus, but the number 20 bus also runs on the same stretch of road, my number 14 predictions will also use the number 20 bus's run times, Because if you're looking at the runtime between, say, stop B and C, it doesn't matter what bus is running on it. It's still valid data for that segment. Okay, so now I've explained how the predictions are made. Now, where do we actually do it? First of all, there are several considerations. Speed. Departure time predictions must be generated and served to the customers in a timely manner, as predictions become stale in minutes. The implementation method must be able to generate predictions every 90 seconds for up to a total of 1,200 buses and their upcoming stops. Storage considerations. Our reporting database alone was growing at a rate of roughly 6 terabytes a year. Scaling. With each bus line having an average of 30 segments and 30 stops, the system must be able to generate over 20,000 predictions a minute. As the bus service varies by the day, the system must have the ability to auto-scale to save operational costs. So more resources can be allocated to handle peak loads, but must be released when load reduces. So based on those considerations, we decided doing this on-prem was not feasible, so we went to a cloud-based platform. Since TransLink is a Microsoft Premier partner, the decision to go with Azure was pretty easy. So we used Microsoft Azure. Technically, it had what we're looking for. It's pretty easy to use. We knew scaling would be a huge issue, so we wanted to use containers and container orchestration technologies. As a Premier partner, we had expanded access to Microsoft technical support and consultants. We would leverage Azure cybersecurity to make the system quite secure. They had options for DR. And my own team of developers had experience with Azure already, so it was a fairly easy transition for us. So now that we've developed all of our machine learning algorithms, and we created and deployed all of the infrastructure in the cloud, how do we know all of this even works? So since we were new to machine learning, we didn't want to take the risk and change the predictions for all of our bus routes right away. So we chose 13 test routes to try it on. Now, these routes were chosen based on several different criteria in order to ensure our models were robust. So here are the different criteria that we picked the routes on. Now, if the models were successful for this variety of routes, we were confident that we could scale out to all the other remaining bus routes. Results. So after gathering a few months of data from the pilot lines, we were ready to analyze the results. Here's a sample result from one of the pilot lines. This graph shows how accurate our previous predictions were over the course of a single day. So the y-axis is the amount of time the prediction deviated from the actual bus departure time. The x-axis is the hour of the day, and the gray line is the actual bus departure time. Now the red line on top, that's the scheduled time. This performed the worst. It was regularly 3 minutes or more off the actual time for this particular route. The blue line here is the original RTTI prediction. This green line here, this is a blended prediction of RTTI and machine learning prediction, because sometimes the machine learning prediction is not always available, so we may blend it with the original RTTI prediction. And finally, the yellow line on the bottom is the machine learning prediction. It is around 1 minute off of the actual time. So as you can see, it's far more accurate than the scheduled or RTTI predictions. Now remember that graph I showed earlier? Here it is with the machine learning data. The blue pyramid was the RTTI predictions. This new orange pyramid is the machine learning prediction. Previously with RTTI, only 53% of the predictions fell in the on-time green window. With machine learning, now it's over 80% of the predictions are in this window. 81% of RTTI predictions fell in the plus or minus 5 minute OK window. With machine learning, this is almost at 95%. And remember the 20% of customers we left in the dark with RTTI predictions? That's down to 5% with machine learning. So to further quantify the results, we had less error and we had less wait time per boarding. So, for that we were estimating the number of people at the stop and multiplying that by the average time they had to wait. So, it's a lot less waiting time per boarding. So needless to say, we were getting a lot more smiley emoji tweets and a lot fewer angry ones. So the results were really good. Now, does that mean we were finished? No. Now we need to maintain and support the system. So there were several operational considerations with a cloud-based machine learning project. So because it is in the cloud, we did have a costly Azure bill every month. So when we started, it was roughly 30,000 Canadian a month. And we've actually cut down on it quite a bit, and this is how we did it. So we optimized code to reduce VM usage. We use Kubernetes to auto-scale the clusters based on need. We're going with cheap cold storage options for data archiving. And with Azure, you can actually reserve resources, and this would you can get up to 70% savings with 3-year reservation, depending on the resource. And finally, we were turning off and deallocating unused resources. So with the cloud, it's extremely easy to spin up VMs and allocate storage, etc. But it's also equally easy to forget about them too. So, a big key is remember to turn off all your cloud resources when you're done with them, especially with like dev and test environments. Like any machine learning model, predictions from our models will drift over time. So the system must have the ability to automatically detect when models drift beyond an acceptable threshold and trigger model retraining with more recent data. If you do not do drift detection, your predictions over time will get worse and worse to the point of being useless. And with over 18,000 sets of machine learning models should have version control. Model lineage information must be traceable to allow future investigations and reproduction of models if required. This allows you to examine why some models behave better than others. So here's a very simplistic depiction of the drift detection workflow. So to start, did the drift detection system consistently detect prediction times that were outside the acceptable limits for a particular model? If so, we need to retrain that model. So that model gets retrained with a new set of training data. Once that's done, we score the model and with test data to see how it performed. If the model meets our criteria, then it's approved and gets promoted to production. If not, then we may need to update the model and retrain again. So this is just a very quick and dirty way of showing how we do drift detection and model retraining. So how long did all of this take? So we partnered with Microsoft in Q2 of 2018 for a simple proof of concept on a single bus route. So Microsoft helped with the initial machine learning model design. In 6 months, we had enough experience to develop our own more advanced machine learning model. From Q4 2018 to Q1 2019, we developed the infrastructure on the cloud and then applied the machine learning predictions to the 13 pilot routes. After this, we thoroughly analyzed all of the data gathered from the 13 pilot routes. Once we were confident the machine learning models were working, we expanded the infrastructure to support all the remaining bus routes. And now that it's deployed to all our bus routes, we had to maintain the system. So we're currently implementing drift detection and optimizing the cloud costs. And in the future, we'll be looking at improving the machine learning models by adding more factors. And so what's next for TransLink? So as shown in the project timeline, the next big improvement is adding more data points to the machine learning model. So this could include things like traffic data, the bus driver. Some drivers are more passive or aggressive. Some drivers may be more experienced on a given route. Special events such as parades, sporting events, etc. And we're also going to continue with cost optimizations. As a taxpayer-funded organization, we are quite sensitive to costs. And finally, we will continue to monitor and improve data quality. Finally, after all of this, you may be thinking, maybe my organization can benefit from machine learning. Now, before you go down that path, you need to answer the following questions. Do you have a lot of data? Remember, each of our stops and segments each required a minimum of 500 events before we could generate an accurate model. Is the data cleaned and validated? Garbage in, garbage out. For example, do you have an archive of all the actual stop times for all your buses? How accurate is that data? Do you have a business objective that is measurable with data? Does your team have the correct skill sets? So it's not just programming and statistics, you also need analysts to collect and interpret all of your results. Is the necessary computing power and storage available to you? Think of the costs associated with these as well. And do you have the ability to do drift detection? If you don't do this part, your predictions will degrade. If you answer no to any of these, you are not ready for machine learning. If you answer yes to all of these, then machine learning might be right for you. And that is it. Thank you.
Thank you, Ron. That was great. We've got quite a few questions.
All right.
Just show my screen. Okay. Oops. Oh, I got the question. Yeah. First of all, I have to apologize. I'm a little rusty on running things, so I didn't hit the right button, so people couldn't hear the first couple minutes. But
sorry about that.
So sorry about that. But it's and the interface on a little screen is kind of difficult. Okay. Question: how is the system updated to show predicted departures on VMS signs, apps, and so forth? So just discuss how the information is actually distributed. Was that
Okay.
Did that change in any way?
Yeah, so we're actually publishing our predictions through GTFS RT. And so originally our predictions were based on the RTTI. And so when we added the machine learning component to it, it didn't change our GTFS feed. It just made the predictions better.
Okay, good. Yeah. And in terms of how far in advance are these predictions being made? The answer is important to judge how good is a 1 minute deviation.
Right. So I believe we have a floating window of like 4 hours into the future, but we may be shrinking that down.
Wow. Okay. That's
yeah.
That's good. And I guess I have a question. There's quite a few others. I knew there would be. But did you? I guess have you taken this information as an input into the scheduling system itself to get more accurate schedules that reflect all this machine learning?
That's a good question. So one of the groups within TransLink that sponsor this is the planning department, and so they're actually looking at this data.
Because one would think it would give much more accurate running times.
Yes, yeah. So we are analyzing that data for the purposes of improving scheduling and all that.
Okay. Question: how are the 18,000 models aggregated?
So I did leave out an architecture diagram which shows how we do that. So based on the line, our system will actually pick and choose which models that represent that line. And so that in a nutshell is how we do it. So we have enough information on the line, and then we pick both the run and dwell models that represent that line. And so we do this for every single line that's out there.
And is this also how you do the blending?
So the blending, you're talking about the blending of RTTI and machine learning?
Yeah, because you're saying to save resources, you're not using all the models, or you're sort of merging them to some extent with the RTTI.
Correct. Yeah. So some segments or some dwells will not have enough data for a machine learning model. So in that case, we'll either go with scheduled data or RTTI data. And in some cases, we'll have a mix of both, which is where the blended comes in.
Okay, but why would there not be enough data? It's because of the
Oh,
AVL
some
system itself was down on routes or things like that?
no, some buses just will, like some buses will be running like every other day, for instance, and you just won't get a lot of data. And recently we had a new bus route, 6 new bus routes launched, and so for a lot of those segments, we did not have any data. So it took us, I forgot how long it took us, but it took us a little bit of time to compile that data and then generate the models. So the first little while, we
Oh,
did not have machine learning for new bus routes.
okay. Here's a follow-up question to the previous question about the how much in advance. So the question is, did you mean to say that the system can predict a bus within 1 minute deviation 4 hours ahead?
No, so we generate predictions up to 4 hours in advance. So if you're at a bus stop, you can actually get a prediction 4 hours into the future. Um, and naturally, as you get closer and closer to the bus time that's coming to you, that prediction, it's always being updated. So that prediction gets more and more accurate the closer you are to that time.
Yeah, I understand. 4 hours seems very long. I thought it was typically just like 1 hour or so.
It is, and we are looking at that. Yeah, so we may be reducing that.
Okay. Okay, let me try to read one. Um, uh, okay, I think this is sort of related, but the histogram that was shown for prediction accuracy, how far out were the predictions in the histogram?
How far out, like how, actually, let me pull up that histogram. Um, so that goes all the way
Wait,
to, I
wait,
think, plus
here,
or minus 10 minutes for that histogram.
a second. Let me just give you control. Sorry. Oh, oh, okay. Thought you were bringing up the histogram.
Yeah.
Um,
Can you see that?
there you go. Yeah, yeah, yeah. We can
Yeah,
see
so
it
that's
now.
plus or minus 10 minutes on either side.
Okay. Um, question I have is, did you get any insights into what were the causes of the major problems on the tail ends of that distribution? Why they were so far off?
That's a good question. I'm trying to recall some of the reasons that we had. Um, yeah, I can't think of anything off the top of my head for like the
Okay.
extreme, like the plus or minus 10 minutes.
Yeah, yeah, yeah. Okay. Okay, another question. Are there any operational cost savings, other benefits provided other than making customers happy? Example, well, example is for saving a bus by adjusting the schedules. You said that's just being looked at now.
Yeah, our primary business objective was really making the customer happy. That was our primary objective. And we are looking at this other data for potential uses as well, right? So I think there's a lot of uses for this data.
So, yeah, so is this, I mean, is the data that you're getting, I'm sorry, I was trying to understand, is it off the AVL itself or because you have that separately from the machine learning?
Correct.
Yeah, okay. Um, okay, how big of a role did weather play as an input to the ML models and how did it affect the results? And I had a corollary to that is I was surprised you broke it down, the weather in the region down to, what was it, 11 or 13 zones. Did that
13
really
regions,
make a
yeah.
did that make a, was the weather significantly different between the 13 regions?
It was different enough for the 13 regions, and the reason we did that is performance related. So so what you could have done is just make an API call to Dark Sky for every position that's out there.
Hmm.
But what we did instead was just, for a particular city like Richmond, we would just cache that data. So every call that was in the city of Richmond, we would just use that cached weather value.
Yeah, got you. Yeah. And how did weather compare to other factors that you took into consideration in terms of its importance?
So if you're familiar with Vancouver, it does rain a lot here, and we
Yeah.
do have the occasional snow days. And so, depending on those days, it was an important factor.
Okay, good. Yeah. Um, what were your, I'm not sure, I don't think I asked this before, but what were your criteria for the drift detection?
So one of our criteria is it better than RTTI? So we're still generating our RTTI predictions, so we still have that. So the criteria is if it's worse than RTTI, then we should probably retrain.
Yeah, and I'm surprised that you really feel that the drift is essential, that the models lose their accuracy over time.
Yeah, I mean, the system's been up and running for a few months now, and we've seen roughly 10% of our models need to be retrained.
Oh, okay, that's pretty often. Okay, all right, get some more here. Oh, here's a I guess you mentioned you're thinking about other uses of the data, and I was sort of curious what other potential uses you've been thinking about.
So this is more of an operational thing. So we do have um, uh, other systems that use prediction times, and so this would just kind of trickle down for that.
Okay. Uh, oh, okay. Here's a long one. I think we partially answered this, but I'll read it anyway. The graph shows prediction variance of plus or minus 10 minutes. But how far in advance of arrival is the prediction being made to be off by the amount shown in histogram? And is that snapshot relative to actual arrival time or scheduled arrival time? We would assume that the prediction variation would be 0 minutes at the time of arrival at the stop, right? Right?
Can you repeat that question?
Yeah, I'm not sure I totally understand either. And uh, is the snapshot relative to actual arrival time or scheduled arrival time?
This
Um,
histogram right now?
yeah,
So that red line is the actual.
okay.
Yeah.
Um, how many, question that I had, how many experts in machine learning do you have on staff in your staff?
Uh, so we started off as machine learning novices, and I don't even know if I'd call ourselves experts right now, but we're still learning as we're going. So we do have some data scientists on staff, and we do have some software developers that focused on this application quite a bit. So um, yeah, it's not a lot. We don't like my team is not that big.
Yeah, but that raises a general question that I and colleagues, I see the industry has gotten to a point where they've got the quality control. The quality assurance of the data is what people struggled with for years, and then they can start doing data mining, data fusion, various
Hmm.
things. But they need both the tools and the expertise. They need data scientists, and that still is a fairly rare occurrence among transit agencies. I'm sort of curious how, and they tend to be gobbled up by high-tech firms.
Hmm.
How hard is it and Vancouver is a pretty attractive environment. Sort of
Yeah.
curious how hard it is, but to hire data scientists.
Um, so the data science department isn't mine, so I couldn't really tell you how hard it is to hire a data scientist. But software developers with machine learning, that's quite difficult to hire for.
Okay, I'm not surprised. I think we covered most of the questions. Oh, okay, no, you've covered that in terms of the. So you are working on the. Well, those new factors you had a slide
Hmm.
with other factors being considered.
Yes,
That that means starting from scratch to rebuild all the models, doesn't it?
you will have to rebuild the models. Yes.
Yes. So that's not a trivial undertaking.
No, I mean, but for us, we've already set up the whole pipeline, so it's
Okay,
much easier this time around. And then the first time
right,
where we
right.
had to build up all that infrastructure and whatnot. So, for us to do
Yeah,
this, by adding a few factors, much easier. I mean, yeah, again, it's not trivial, but it is, it's
yeah,
simpler this
right.
time
You're
around.
not setting up the whole framework for gathering the data and
Exactly.
what data to collect and so
Yeah.
forth. Yeah, I could see that. Could see that. Um, uh, Overall, did senior management appreciate I guess uh, the amount of, the results based on the amount of effort it took?
Yeah, definitely. We're very focused on customer satisfaction here. So, for senior management to see a lot of that positive feedback, like I think they're quite happy with this as well.
Good, good. Well, and I guess that's part of the issue we're facing is that we need more use cases of why data analytics are even worth investing in.
Hmm.
Here's another question here. Is your, okay, oh my goodness, keeps on jumping in. Okay, how long does it take to complete the training of each model?
If I recall off the top of my head, each model takes, I think, 90 seconds to 2 minutes to retrain.
Okay. There's another related question. Presumably, it's way more expensive to train the models than to run them. Can you please elaborate on where most of your money is being spent computationally?
So, so that's a really good question, and that's something we had to discover for ourselves because we had no idea what any of this would cost. So the retraining does cost money, but you only need to retrain. Like I said, we recently retrained 10% of our models, so you only need to retrain for that amount of time, and that's it. Now, to keep the system up and running, you have to keep your Kubernetes cluster, your databases, all that up and running. So what we're finding is the operational costs far outweigh the retraining costs.
Hmm. Oh, just for the layman, can you explain what the cluster technique you just mentioned were?
Right. So Kubernetes is our container orchestration platform. So what Kubernetes does is it kind of scales up your VMs, your virtual machine. So if you're requiring more computational power, Kubernetes will actually do that automatically for you. So that's what we're kind of using it for.
Okay, good. Um, Different question. Is your pipeline code an open source project?
There are discussions to make this project open source, and I haven't had an update on that yet.
Okay, I'm sure it would be of interest to others. You should also mention that you wrote a paper for TRB that
Yes,
discusses
we
this.
we published a paper with the Transportation Research Board, and that was published in January. And we actually sent a couple people to present in Washington, D.C. for that.
Right. Now I should mention, uh, let me see if I can do this, because those that it would it be if people are interested in that paper, could they contact you? Let me
I
see.
believe we published it through the TRB, so I think you can get it from the website.
No, you can't. I'm
Oh, you
actually
can't?
quite
Okay.
involved in
Okay.
TRB, and they made a decision this year not to. Anyway, it's a long story, but only things available from TRB are abstracts and presentation slides for most sessions. So not
Okay.
the paper itself.
Oh, okay. That's surprising.
Um, yeah, it has to do with TRB trying to make their publication more competitive with academic journals.
I
So
see.
it's complicated. So I don't know how we could um, you well, I don't want to burden you, but you could send it to me then, or you could have people contact you directly. Trying to
I
figure
think I
out.
sent you a
Well,
copy, Brendan.
yes, I have a copy.
Yeah.
So
So I
people can.
mean, I don't know if I mean, will the TRB allow us to freely
Yeah,
handed
no,
out to?
no,
Okay.
that's what they said, is that people
Okay.
could contact the authors individually, which is very painful,
Mm-hmm.
and to get papers. So there's no copyright or distribute. There's
Okay.
no,
Okay.
as long as you're okay with it, it's fine. There's no none of that for papers just that were just
Mhm.
presented at TRB. It's for the ones that are going to appear in the transportation research record that
Okay. Gotcha.
they're trying to
Yeah.
change.
So you've got the copy there.
Yeah, okay. I'm trying to well, I think everyone would have gotten my email because all these are people that were on the APTS committee list. So just please contact me. Now I'm trying to, sorry, I was trying to bring up another slide, but I'm having a little trouble here. I think we're almost at time. Let me just see quickly if there's any other questions. Actually, you know what I'll do? I'll just put my email. I just sent out a notice. Hopefully people can see it with with my email. So just let me know if you would like a copy of the paper. Okay, I think we've come to the bottom of the questions. Quite a lot of questions. I knew there would be. So Ron, I'd like to thank you for doing this presentation. And it's a fascinating project, and would like to appreciate that we had a very good turnout. So
All right. Thank you for
let's
having me.
keep in touch. Okay, thank you very much, and thank you everyone for participating in the webinar. Thank you. Okay, bye.